In this lesson, we're going to be looking at the situation where a coil, no battery, just a coil, is being pushed into or pulled out of a uniform magnetic field from a region of space where there is no magnetic field. So we're taking the case of B equals 0 out here, B equals 0 out here, and the coil is starting out here in this example. We're being told it's going from a region of no B field to a region of B field into the paper, and what's more, we are told that it is moving at constant speed. So we'll get to that, how that comes into play in a moment. Now, before we go into the mathematics of this problem, I do want you to please put into your notes this statement here right at the top. So even without having to make a mathematical analysis of what's going on, I want you to know that qualitatively, in this type of situation, the coil will always resist being pushed into the field, and it will also, once it's fully in, will resist being pulled out of the field. Now, in terms of why that's the case, we're going to see exactly why the induced effect resists this change. And but based on Lenz's law, it kind of makes sense to us, because we know from Lenz's law that nature wants to induce a current to try to keep the status quo, to not let the flux change. And let's see what's going on mathematically. We'll get a better understanding, I think, as we go along. So the first thing you want to do when analyzing this type of a problem is to qualitatively just address whether the current, the induced current, is going to run clockwise or counterclockwise in the problem that you're looking at. Well, in this case, we are given that the coil is moving to the right, so it is going to be gaining flux into the paper. Well, Lenz's law wants to put a stop to that. So it is going to induce a current to make B field coming out of the paper. So by Lenz's law, we get the counterclockwise movement. I induced runs counterclockwise. The induced EMF will also be counterclockwise to fight the change. Now, our coil, as I said, does not have a battery. Some problems, not this example that I have in the notes, but let's add it in here just so you'll realize that for some problems, the coil, which does have an inherent resistance to it, remember resistance equals resistivity length times area, so some problems will actually show a representative resistance in here representing the total resistance of the coil. So let's put that in for our analysis as we go down here. All right, so we said that the coil will always resist being pushed in or pulled out. Well, I have here pre-annotated that the force is going to be to the left, but let's understand all the forces acting on the coil based on the magnetic force is IL cross B. So the magnetic force is IL cross B. It turns out the only region of the wire that's actually going to contribute to the affecting the overall motion is the highlighted region here. So the current, the induced current, times the L now is our W, length times width, so it's our W, cross B external. Now when you're looking at the magnetic force, you do not use B induced, always use B external. So when we do our right-hand rule, I induced, right? IL cross, or IW in this case, cross B. Do it with your right hand with me. Palm facing down, make a fist, thumb to the left. So that's why the force, the magnetic force, is going to work against the force push. Okay, so let's get the expression for the flux. Now getting the expression for the flux is a little bit tricky in that the flux is going to be a function of time, because we know the flux area, right? This area is going to be changing as this x distance, right? This base gets bigger as the coil is pulled to the right. So even though we have our B dot NA, where the B is B external, it's into the paper. The N hat is, by convention, right-hand Cartesian coordinate system out of the paper, cosine of 180. So my flux is going to be negatively valued. We'll see why that makes sense in a moment. Area is length times width, so we have length times width. And the length is changing as a function of time, and this is where, for this problem, we are told it is moving at a constant speed. Speed equals distance over time. So distance equals speed times time. There's how we get our time into our flux as a function of t. So you want to keep in mind that even though the x may look like a static parameter when the problems are presented to you, it is not. It will be a function of time, in this case, velocity times time. So we have our flux. Now, when we take the induced EMF, it's negative d flux dt. And look, that negative d flux dt is going to end up giving us two negatives, the negative in the definition and the negative for the flux. So our two negatives make a positive, so it is going to be a counterclockwise induced EMF. That's a curl, right-hand curl, thumb out of the paper. And when we take the derivative of t to the first power just gives us our b omega v that we get for our voltage. And now let's introduce our Ohm's law. Remember, we put that resistance in there because some problems will ask you to utilize Ohm's law to get part of what they're asking you to solve for. So put an IR in there as well. Okay. Now, the last thing we're looking at are the graphs of the equation. So if we take 3 here and look at our equation for flux, so this is the flux as we're moving into the B field. So that's why, please get this into your notes. So the T here, that T1 is important. That's the time it takes from time 0 when it begins, first hits the B field, till it gets all in. The flux is changing according to our equation 3. Okay, and that's the negative slope. Once the coil is all in, the flux remains constant. And I hope, as you can imagine, now we're not going to solve it, but if you want to solve it yourself, take a look at what happens when the coil gets pulled out and you begin to lose flux. So now nature, Lenz's law, wants to make I induced into the paper as you begin to lose flux into the paper, and that will say, so I induced wants to be into the paper, so we have IL cross B, so now the induced current is going to run in this direction, and when we do IL cross B, our magnetic force is going to be to the left, again, resisting, as we said, resisting the coil being pulled out. So the flux is now positive. The voltage will then go to negative for our counterclockwise. And for the last part, the induced voltage, we simply have our constant BWV. So very typical question for Faraday's law unit. So please make sure you get all of the annotations down, and of course ask questions if you have to or have any when we're together with class.